All right, so in this topic 1 video, we're going to lay the groundwork for the rule that will become known as the chain rule. The chain rule is going to be useful in deriving composite functions, which we haven't looked at yet, at least not in talking about derivatives. So in order to create that rule, I want to just get started with an example over here on this extra page. So let's get started just with an example of a composite function so that we can remember what those are. So I'm going to say y equals the sine of x squared plus 3. So the reason that we call this a composite function, I know from talking to you all in class, this is not going to be a big mystery. It's because we have essentially an outside function and an inside function, both of them recognizable but different. So, for instance, the outside function here is sine, and that's an operation, right? Normally we see sine of x, but this is not sine of x. This is sine of a bunch of stuff on the inside. On the inside, we have x squared plus 3, which is also a recognizable function, kind of a standalone function. And but it's different than like a typical, oh, let's just graph. What does the graph of sine look like? When we say that, we just mean sine of x. We don't mean sine of x squared plus 3. So by looking at this in the blue, or what's underlined in the blue, I want you to think of that as the outside function. And the portion that's underlined in red, we're going to think about as the inside portion. When this doesn't look, I'm assuming you're looking at this and not thinking, oh, that's a really crazy function, because sine of x squared plus 3, it's not really, it's not something that gives you math anxiety just by looking at it. However, there is a bit of a problem here, because if we were asked to find the derivative, to take the derivative, we'd start going through the list of tools that we have. Well, we know how to take the derivative of sine. The derivative of sine is cosine. But we don't know how to take the derivative, that's sine of x, not sine of x squared plus 3. Now we also know how to take the derivative of a power function, x squared plus 3. The derivative of that portion is just 2x, right? 2x plus 0. But again, it's not just x squared plus 3 that we're looking at. We're looking at x squared plus 3 inside a sine function. Now, I've heard students say at this point sometimes, oh, well, let's use the product rule. Let's call this part u, and let's call the second part v. That would work if the operation happening here was multiplication. But we know that's not what sine is. The sine function is not a product. It's not a multiplication operation at all. So the product rule is not going to work. So here's where we come to the conclusion that we need a new rule. And so in order to describe this rule, I'm going to make a mathematical statement first. It's one of those ones that probably, if I were to try to explain it going forward, it might be confusing, but I'm just going to give you it as a fact, and then we'll work backwards to check and see if it makes sense. So I'm going to make the statement that dy dx, which is our symbolic way of saying take the derivative of y with respect to x, is mathematically equivalent to this operation. dy du, which I know, what on earth is du? We don't know yet. We'll find out. But dy du times du dx. So don't think about calculus right now. Just think about fractions. As it turns out, this expression for that, or this symbolism that tells us to take the derivative of a function, dy dx, was actually chosen intentionally for its mathematical integrity, for lack of a better word. It actually has mathematical meaning. So take a look at these fractions. dy du times du dx. Well, using our normal rules for fractions, if we think of dy as like an instantaneous change in y divided by an instantaneous change in u, and then du dx as an instantaneous change in u divided by an instantaneous change in x, we can think about these as like variables. So dy is a mathematical value, du is a mathematical value, and so on and so forth. Um, and when we do that, we see that there's a variable in the denominator that's the same as the variable in the numerator, and those two cancel. So du and du cancel, and what we're left with is dy over dx, which is what we have here on the left portion of the equation. So we can see, mathematically speaking, what I've written is accurate. Now, we don't know what it means. We don't know if it's valuable to us, but hopefully we can agree that it's mathematically accurate. Now, by the way, I just want to throw a little piece of information out here that I was thinking about as I was explaining. I don't think we actually talked about this in class, and you might find it interesting. Do you remember talking in, let me just keep this information here on your notes. We'll come back to it. Let's just take a blank sheet for a minute. When you were in algebra, do you remember talking about slope is the change in y over the change in x? I know you remember this because we've talked about it a million times this year already. Okay, maybe not a million, but a lot. And so it's y2 minus y1 over x2 minus x1. But what I want you to think about in particular is this expression here. And we use the term delta y over delta x because we know that this triangle means change in. So it actually usually looks a little like this. So it's our Greek symbol delta, and delta means change. So this is change in y over change in x. Well, I didn't actually think to tell you this earlier, but when we have dy dx, we're using that same symbolism. D is actually like delta, but instead of an average change, which is what delta talks about, an average change in y over, or a, actually you're looking for average change, right? Average rate of change, so change over a period of time in y, change over a period of time in x. This dy represents an instantaneous delta. So these kind of correspond to each other. Dy corresponds with delta y, except that dy is instantaneous, delta y is over a period of time. Dx corresponds with delta x. So, but it's an instantaneous change in x, that's the dx, versus change over a period of time. So, when we talk about dy, we actually are talking about a quantity, the instantaneous change in the y direction over the instantaneous change in the x direction, which means you have an instantaneous slope, right? Instantaneous delta y over instantaneous delta x. Just a cool piece of information, which probably will help us make a little bit of sense of the math here, right? Because really what we're talking about is little instantaneous y change divided by little instantaneous u change times little instantaneous u change over instantaneous x change. So hopefully that just brings some mathematical clarity that I thought maybe I should throw in there. That was a little spontaneous tangent for you. Okay, take that, tuck that away as valuable side knowledge about calculus, and then let's go back to this idea of the chain rule. So we can establish that this idea of dy dx can actually be rewritten into two pieces, du times dx. Now, what does that mean? Du, let's see, can I? Oh, I can undo these little pieces so we can see. Dy du, that means the instantaneous change of the y function with respect to the instantaneous change of the u function. So what that means is, let's think about y equals sine of x squared plus 3 in two parts. Y equals sine of u, and then the second part is that u is x squared plus 3. So we're going to call this u just like we do in like the product rule or the quotient rule. Whenever we have a function that we want to name so that we can use it, we call it either u or v. Well, in this case, we only have one function, so we'll call it u. If we had two, we could call the other one v, but we don't. We only have one. So we're going to call the main one y, which is what we called it to begin with. Y equals sine of u, and then we're going to define u separately as x squared plus 3. So what our little rule here says, that we've decided makes mathematical sense, but we don't know exactly what it's asking for, says if I want to find the derivative of a whole composite function, I should break it into two parts. And first I should find the derivative of the outside function, right? That was the blue. The derivative of the outside function with respect to u, and multiply it by the derivative of the inside function with respect to x. And I should be able to get, or I know I can get the answer, and that's called the chain rule. Let me rewrite that in words. So I'm going to go over to this separate slide, and I'm going to say this is the chain rule. It says if you want to find the derivative of a composite function, we take the derivative of the outside function times the derivative of what's inside. So that's the little phrase. If you need a little quote, the derivative of the outside function times the derivative of what's inside. And I don't know if looking at all the symbolism makes it look like it's going to take a long time. It actually, when we look at it in practice, is going to be one of the fastest rules for us to do, because we don't even have to do all the list out u and v and u prime and v prime. For the most part, we can usually just move through the problem pretty quickly using what we've already memorized about power functions, about trigonometric functions, and so the process is pretty fast. But just for the sake of breaking this up into pieces and letting you take a breath of fresh air for a moment, I'm going to stop there, and I'm going to save the second topic video for showing you what this looks like in practice. But if you need one thing to take away from this all, well, there's a lot of stuff I want you to take away all of it, but if you need to boil it down to one statement, it is the chain rule is when you have a composite function and you want to take the derivative, is the derivative of the outside function times the derivative of what's inside. All right, I will see you in the topic 2 video.